right, welcome back, everybody. Good morning. So as I mentioned last lecture, I said I was going to release the averages and things like that once the person who's sick would take it on for Monday. Well, bad news for this person, it didn't get better. So I'm going to have to ask you to be just a little bit more patient. There is an anticipation makeup date, which is Friday. So until then, you know, a little bit more patience from your end. So I appreciate that. But we have the statistics. So we'll release that come Friday once the makeup has been graded. That's about it. Let's see. Any other housekeeping business that I miss? Any questions about that? Yeah, Ethan.
You mentioned the survey.
Yes. Right. So I was also going to release that right after you get your exam score, mainly because as a scientist, data is data. Information is very valuable. So with that information, it helps you be fully informed, engage how you feel about the pacing of the course, things like that. I think, obviously, if you don't have that score, you're not fully informed, you don't have all the information readily available for you. So unfortunately, that's also delayed until we get your exam scores out to you and upload them to Carmen, because if you think you did really well and you didn't, or you didn't think you did that well but you did, I think having a full picture of all the information is helpful so that I can get your constructive feedback. Okay, anything else? Okay. I also emailed out Carmen, that should have landed in your inbox, about the survey. So yes, the majority, not overwhelming majority, but a majority of the class voted, and a majority of those who voted did vote in favor of moving office hours from Wednesday 11:30 to now Fridays at the same time at 11:30 for an hour. Granted, the next exam is also on a Friday, so during that exam week, we'll move it back to Wednesday so that we keep the same amount of office hours that are available to you. So that would be the only exception. I will make an announcement to remind you of that come exam 2 week, but that's the only other thing, okay? Okay, we left off, and we only really touched upon briefly fracture before we left last time. So I just want to basically start from the beginning because I don't want to jump around too much. Okay, so we started on chapter 8 talking about fracture, fatigue. As you recall from the stress-strain curve, we talked about fracture when things break. Basically, when you apply enough load and there's enough elongation in your material will fracture. So there we looked at stress, strain, usually in MPa. This is usually unionless or percent. And then we looked at something like this. And so fracture occurs right there, typically in X, as we've noted. So that's just fracture. Fatigue, however, and this is something we'll go into, fatigue can occur and your material can fail eventually due to fatigue, even if you're below the tensile strength. Okay, I should put a dot, sorry. Even if you're below, let's say, the tensile strength, okay? So your material can fatigue and fail before then. Then we also talked about creep. So that's when there's a static load, and it could also be at high temperature, right? So we looked at a static load over time. And when I say high temperature, I technically mean at least 40% of the melting temperature. That's the region we're talking about. In your book, it says about 30% to 40%. Most people take it as 0.4 of the melting temperature. That's the temperature you really want to worry about. Okay. We talked about some of the ships, right, that fail due to the material, the metal being brittle and breaking in a disastrous way, like the Titanic. We also talked about other ships, the Liberty II ships in World War II that were built in the 1940s as part of the US-UK alliance to basically ramp up the construction of a lot of ships because we needed at the time. Now, there are multiple failures with the Liberty ships. Not only, the fact that they operated in cold conditions, that's one thing that doesn't help, but the other issue is the weld. So Professor David Phillips, who's going to be coming in 2 weeks to give an expert lecture on welding, can go way in depth about the weld and really the weaknesses at those weld joints. Certainly, if you're scaling up from a few ships a year, like massive ships, if you as the United States, you're building a few ships a year for your military, and then you have this huge war, and now you have to massively scale up to 2,000 ships. You could see where some of the manufacturing issues could arise, and they arose in the welds of the metal parts, right? So that's a huge issue. When we talk about fatigue, we talk about compressive strain, tensile strain. We can also talk about thermal loading, heating, cooling. That will also fatigue a material. That's seen a lot in microchips, and that could lead to failure. So there's a lot of X-ray microscopy and also X-ray diffraction that's done on all these parts. So if you're Intel, you're just cranking through these parts and testing them to see, if someone's turning on and off their computer and just running at 100% RAM or something like that, how taxing is that going to be? And then, of course, also importantly, biomechanics, right? We have now really great intersection between mechanical engineering, materials engineering, biomedicine, right? Plastic surgery, reconstructive plastic surgery, all of that, so that we can basically replace whatever joints you need due to injury or age. The issue is, of course, our body puts the same amount of a load and the type of load onto these replacements, and here you see a hip implant. And so you could imagine the torsion that's happening at the ball socket, and also the screws when you screw them into your bone itself or around your tissue, right? These can become real fatigue issues, and there are really a lot of fabulous papers out there that study this. I talked a lot about load. Another thing that I want to talk about is fatigue due to the environment. This is one of the 11 bullet points that's listed at the end of your chapter that says these are all the mechanisms in which your material will fatigue and fail. And often we think about wear and tear. We sometimes forget that wear and tear is, we forget about the environment itself. So if you're in a highly salty environment, a high saline environment like your body, right, that adds to the corrosion of these parts. So there's, I think it was in the 90s, if any of you have relatives, although I think you were born in the mid-90s, so you may not have remembered this, but, or been alive to remember this, but certainly, there were a lot of parts that were designed very well, but biomechanically, test and tear, obviously ASTM, they had to report all those values before they left for distribution. But one of the things that these bio companies didn't test for was saline corrosion. So basically they did the wear and tear test, but not in salt water. But when you put it in salt water, the corrosion, the fatigue accelerates. And so when you put it in a body, you can imagine what happens. So these things are guaranteed at the time for 10, 15 years. The majority of them needed replacement within a year. That's how bad it was. So there's obviously a massive recall. Now these parts, honestly, they're guaranteed for a lifetime. Granted, if you're getting a hip replacement due to age, a lifetime for you may mean 20 years, 30 years, depending. So, lifetime is relative, but certainly much longer than what we were guaranteeing, in the 90s. Okay. So, there seems to be a synchronization issue with Box because my links are not showing up, but that's okay. They're quite retrievable. So before we go into ductile and brittle fracture, I'm going to post this onto your Carmen page under Chapter 8, Resources and Information. But I just wanted to show you the mechanism from this very old, possibly a late 80s, early 90s movies. But it gets the point across as to what's happening. So let me, okay. So when materials fail in a ductile way or in a brittle way. So you could see right there, yeah. So you could see here a load is being applied in tension and it snaps. So you see this typical cone shape, cup and cone type of breaking versus just cleavage and breaking. So you can see here brittle fracture. So it just breaks off, right? So there's no necking. You don't see the elongation and the narrowing of the area. You just see break. So fatigue, you can apply a load like this, and there are machines that do this for you. Apply stress, compressive and then tensile stress, and then also rotate the bar. And so there are a lot of videos that show this. This video is quite spectacular. They also show you some micrographs of what happens when these things break and at what point and how do they break. Let me see. It's a very long video, so I'm going to skip to the point where it just is illustrative of, yeah, so you could see these voids forming and then just breaking. Okay, so that's one. And of course, I'll post this so that you can watch the whole thing. It goes into great detail as to how materials fail. But maybe more importantly than that is how materials behave at really cold temperatures. So here are two bell peppers. Wow, it really knows I'm in the energy. Okay, so this is liquid nitrogen, very low temperature, negative 320 something Fahrenheit. So it does not at all, you know, our cold days don't really compete with this. So what do you think is going to happen to this poor bell pepper? Let's treat it like a polymer. It was once fibrous. Let's treat it as a thermoplastic fibrous polymer. Now it's been treated to liquid nitrogen. It's obviously very cold. What do you think is going to happen? It's going to shatter. So it's going to be brittle, brittle fracture. Okay. Oh dear. It is exactly what you think it is. Okay. So all right. So that's how polymer behaves. There's another example of polymers. Okay. Now let's go to a lock, right? So if you ever forget the keys to your lock, this is one way of dealing with the situation. Okay, some steel. All right. Okay, clearly it's a lock because you can put a key in it. All right. Now it's soaked in liquid nitrogen. Okay. What do you think is going to happen to this? Now that you've decreased the temperature to something that's really low. It's brittle. The fracture is going to be, yeah. All right. Oh, they did it to two locks. I've forgotten about this. Well, it's true. Always gather statistics, right? You need to be able to repeat your experiment. You can see it's quite a small hammer. Oh, okay, so the piece didn't actually shatter that much, but I think it's also because it was okay, well, yeah, so you can see there just complete cleavage, right? It is a clean break. There is no ductile breakage right there. So you don't see any, ductile breaking, which means you don't see any necking, you don't see elongation and then narrowing and then breaking, you just see the breaking. So it's a brittle break. Okay, it's a brittle fracture. There's a lot of these types of fantastic videos online. Okay, so that's it. Now, if you look at the material after this happens, after fracture happens, you can tell almost immediately how the material broke. One, as I mentioned, is cup and cone. That's due to necking. Brittle is just a clean break. You can also kind of see just by eye, you know, the shimmeriness of a brittle fracture versus a kind of a dull surface for a ductile fracture. Okay. As I said, there's some elongation, and if you notice elongation, if you have a monitor set up, or if you're servicing this material and then you bring it in just to check on it, you can do X-ray microscopy, X-ray diffraction, and you could see, there's some changes in the structure. You could probably just take this to an optical microscope, to be honest. You don't have to go down that far in resolution, but you can see just by examination, you're going to see, eminent failure. The problem with brittle fracture, of course, is that it happens very quickly, and so you might not see this as you're inspecting a part. So that's pretty dangerous when it comes to materials failure. Right, so we see here some more examples. Brittle fracture, it's in fragments. There's very little deformation, if any. Ductile, there's large deformation. You could see it coming. This is a good thing. It's better to catch a flaw, right, before it ruptures. So there's some bit of warning there. There are also ways of testing materials. If you just machine something, you want to see what kind of impact, what kind of toughness it is. The impact energy that it can absorb, you do these types of very standard materials and mechanical engineering type tests called the Sharpie impact test. So you lift the weight and then you drop it, and based on MGH difference, the height and difference of how much this pendulum swings, then you could back calculate how much energy has been absorbed, right? So you could talk about a material's toughness that way as well. And as you recall, the toughness is the area under your stress strain curve. Okay. And Professor Glenn Dane, who does this a lot, he'll come in and talk about these fun types of experiments on failure. You can manipulate the stress strain curve of a material or the mechanical properties of a material by either heat treating or alloying, things like that. So we've already seen from the YouTube video what happens, to metal when you drop the temperature, right? As you mentioned, it goes through brittle fracture. So you can see here the stress strain curve at room temperature, 25 C. You can see it's quite ductile, right? So if we looked at the permanent strain at fracture, if this is the slope, voila, that is your ductility. And then you could see that ductility decreases at negative 100 C. And then basically you have elastic type of behavior and then just fracture. Okay, it's going to be quite brittle. Okay. So what you've also noticed is the slope here doesn't change. So the modulus, the stiffness doesn't change. You've just changed the ductility in a material and the toughness in a material, but you haven't changed its stiffness at all. Okay. We left off on this plot. So here you want to see, how do I improve this plot? How do I improve the ductile to brittle transition temperature? What you want to be operating in is, above the transition, because you want your material to be ductile so that if there's going to be a rupture, it's going to be, you have some warning, there's some time. So you can add in, let's say, substitutional components. Here it's a particular steel, so if you add in some substitutional manganese, you can actually decrease, as you can see here, from 0 to 0.5% to 1% to 2% manganese. You can decrease the ductile to brittle transition temperature. So now your material is safe to operate at, I would say, negative 25 C and above. Now, safe is a highly nuanced term. So if I'm just looking at this transition, then this is the predictor, right? Is it above or below this ductile brittle transition? Above, it's going to be ductile. Below, it's going to be brittle, okay? And you can see that here. The impact energy, you see it's quite low below this transition temperature, where it's quite high above, right? It can absorb a lot of energy above this transition. So it can plastically deform and give you some sort of warning, okay, before rupture. Same thing with carbon content. Here, if it's steel, it's iron-based. So if you're adding carbon, a small atom, into iron, now it's interstitial substitution, but you have similar effects. So if you go from 0.11 to 0.2, you can actually, actually here you're actually increasing the, okay, well, it has well, there are different phases as well. Okay, so that should be nuanced. So substitutional manganese is one thing. When we get to chapter 9, we'll also talk about the different phases that that steels will go through when you add in carbon. But anyway, so let us put a paper clip here and come back to that, because this is a little bit more nuance in this. But the general behavior is, you know, one way you can increase brittle behavior or decrease brittle behavior based on what you add in. So it actually goes back to the phase diagram and not just temperature alone. So it's a little bit more nuanced than that. So let's come back to that. As temperature increases, what was the second part of your question? For this? The impact energy change, right. So it depends on the temperature, and by the temperature you mean ductile to brittle transition temperature, right, or DBTT, right. So yes, above that temperature for a certain composition of manganese in steel, yeah, it does change. So your impact energy is much higher in the ductile region than it is in the brittle region. Okay. So we talked about fracture. Let's talk about failure and fatigue. So a material can fail if it doesn't perform as it is designed to perform. Okay. So if you build a table and it breaks, it has failed, right? If you design a chair and you sit on it and it breaks, it has failed, right? So there, you don't even need cyclic loading. It just failed, okay? So, but there are also different mechanisms in which materials can fail. So we talked about creep. So if you stress your material at high temperatures, your material can fail. If there's a crack or a flaw, as is in any real material, your material, this crack can propagate, so it can grow in length, and this growth is also accelerated as the crack gets longer. That can lead to failure by mechanism of fracture. And then you can also just wear out a material. So that's fatigue. That's cyclic loading, right? Continuous compressive, tensile stress and torsion as well. You can definitely fatigue your material and it will fail that way, even if your load is well under the tensile strength, okay, of a material. So many ways a material can fail. 3 out of the 11 points that are brought up in your book. So if you're thinking about, what is worse in life, having some small cracks or one large one, it really depends on the history of the material and the future of the material. So what I mean by that is, if you have some small cracks, that might not be so bad, even if you have a lot of them, because these cracks are tiny. So I'm comparing two regimes where if you have one large crack that's above some critical crack length, that would be a very bad thing. So you would not want that. You might want to prefer a bunch of tiny cracks that are static, and at least in compressive strain, they don't, nothing will happen, right? Obviously, if there are a lot of tiny cracks and this material is going through wear and tear, right, it's in service, then those small cracks will also become a problem over time. But if you just take a snapshot and you say, okay, this material has a bunch of tiny cracks versus one large one, in that particular situation, I would take the tiny cracks because of what's called stress concentrators, okay? We'll look at stress concentration and also fracture toughness of a material. Those are two different things, even though they both have the letter K as the representative notation. So let's talk about stress concentrator. If you have a crack, the mathematical formalism on how to model a crack and how it propagates is with a sphere or a circle in this case. So in 2D here, XY, you see this crack as being representative as a circle, Okay, so you can have just sort of a nice round circular crack, or you can have a really extreme thin crack. So that's more ovalish. That's the example that you see on the right. Okay, so then if you apply some stress, this sigma naught, you know, how is the stress right at the tip of that crack going to be? So it's as the name denotes, it's concentrated. It's a stress concentrator. So even though as an engineer you know the applied load, the stress that's right at that tip can be immensely higher than what you apply. So the way you take a look at that is if you move this over here and you take a look at this ratio, you could see, okay, what is the K? What is that ratio right at the tip? You know, how much is the stress concentrated? It could be 15 times as high, it could be 20 times as high. So even though, let's say you apply 100 megapascal, it could be 10x that, 15x, 20x that, right at that crack. And when that happens, it can actually propagate the crack growth and actually fracture right at that point, even though your applied load, sigma naught, is well below your tensile strength. Okay, so if you're working with steel, some of the steels we've been working with, right, their tensile strength is what, 500 megapascal, 600, 700. So you think if I apply 100 megapascals, that should be okay. It is not. If it's a ceramic, right, you could see ceramics don't have plastic deformation. So if you're applying a load, even though you say, well, it's still below that yield strength, it's still going to be concentrated, and it's and the relationship is this equation right here. Okay, and so this rho at the tip is just your radius of curvature. So if you have a circle, your radius of curvature is just the radius of your crack. A equals A. Okay, so it's A divided by A, which is just 1. If your crack is more ovalish, right, it's a smaller crack, but you have a smaller radius of curvature, but it's longer, right? That can concentrate the stress more so. And you can do this analytically by, you know, going to just Wolfram Alpha and just showing it. And you could see, you know, the applied stress versus, you know, what you experience for a crack. Let's say this is A. If you apply something here at the tip of the crack, if you say, okay, this is my internal crack, that's the oval there, you could see the stress right at the tip could be much higher. And so this could be 10x, 20x, it could be much higher than what you applied, okay? So that's the stress intensity factor, okay? This Y here I haven't talked about, mainly because it's geometric and also materials dependent. A lot of times we treat it as 1 for simplicity, because we really just want to look at, okay, if I have some applied stress, some nominal stress, what is going to be my K, right? And that's based on the applied stress and also your crack dimension. And the way we treat surface cracks versus internal cracks, very simple. Surface crack, you just measure the length of your crack, that's A. So this 1.1 here, that's materials dependent, okay? It could also just be 1. Your internal crack, we treat that as 2 cracks. So if you consider, right, if you just block off this part, this looks like this, right? So we treat an internal crack like it's just 2 surface cracks. So your crack that's on the inside is 2 crack length, because we're treating it as 2 cracks. Whereas your surface crack is just that. That's how we define crack length. So internal is 2, or if you're given the internal crack length, then A is just divided by 2. Okay, so if you're given an internal crack length, that's really, you divide that by 2. Sorry, your length is 2A. So I'm sorry about that. So if you're given a length, you have to divide by 2 to get your crack length. Okay? So here, this would be the L that I'm referring to. Okay, L is 2A, or L divided by 2 is A. That's how we normalize surface cracks to internal cracks. Okay. So we talk about these cracks, we talk about these flaws. Really, the main question is, when will this material fail? That is when we need to talk about the other K, which is K sub C. In your book, it also talks about K sub 1C or K1C. It's spelled like I, though, so, you know, like the Roman numeral 1. So this is the critical fracture toughness. This is the critical K. So if your stress intensity factor is greater than your fracture toughness, so Kc is different from K. Okay, K, your stress intensity factor, is basically the ratio of the stress tip that's experienced right at the versus the applied load. So your fracture toughness is the toughness of the material. How much energy can it absorb, right, before this is going to fail? So we can calculate that by, to reiterate, the applied stress, and we take a look at your flaw to begin with, your crack length. Okay. So if it's greater than your fracture toughness, the material will fracture and fail. If it's not, then your material can withstand that applied stress, and things are okay. Okay.
What is Y again?
This is a materials property. Often we just treat it as 1. Okay. If it's not denoted as so, like examples in your book, it's 1. But your book mostly says it's 1.
I'm aware of the Solon column. Could you go back to the previous slide real quick for a sec?
Wait, what?
I'm aware of the Solon column. Could you go back to the previous slide for just a second?
Oh, okay. What's the question?
I'm good. I just need to
Oh,
get
okay.
some formula.
Okay. Right. So, condition. Cracks are stable and will not propagate if it's below Kc. Yeah?
I had a question about the units of K. Why did we choose to have the
Square root.
square root instead of just squaring it all?
That's a great question for our professional ancestors. No, I mean, I say that in all honesty. It's historic. Right. Square root of meters is not something that our brains process well, because we process unit like meters well. Why? I don't have a really good answer for you. So we're in the same boat there. But I agree. I mean, you can also square it and, you know, same. But then you get megapascal squared. Okay, you know, but okay. So we want to know, will material fracture, will it not fracture? If you have an applied stress and you know your crack flaw because you've done X-ray diffraction, you've looked at it under a microscope. If your crack is big enough, you could see it under an optical microscope. If it's not big enough, you get into a scanning electron microscope, right? These are the instruments that we use for failure analysis. If it's below this line, this curve, there will not be fracture. So it's a safe area to be operating with. There are statistics, though, as to where is safe really, because when you do these actual measurements, you make a measurement here, you have your specimen, that's a standardized size, right? All standardized dimension. You do these torsional tests, you do the compressive tension, applied stress. Where it will fracture, you collect all this data. The error bar is actually something like this. So if you have an applied stress that's here and your crack length that began was, let's say, here, even if it's plus something and minus something for the crack length, it could fail. That is the cusp, okay? Now, if you're in this regime, the error bars in real life tend to be like this, okay? So let's say that's your data point. Statistically, you could fail because it could be out here as well. So when we get to this applied stress, it's less certain. So even though, oh, it's a much lower applied stress, you're more likely, you know, it's probably not going to fracture. That's actually not so true. And so we, what typically happens is when you engineer the material, you just sort of rate it a little bit more safely. You say, okay, just don't operate, under these conditions. But anyway, we'll get to a plot that looks sort of like this as well. Okay, so right, so a stress versus crack, and then right. So you could also flip the equation, and if you plot crack length versus stress, same thing. There won't be any fracture if your crack length is, let's say, quite small, and you also apply a small load. That's going to be your data point there. Probably not going to fracture. If you apply a lot of stress and your crack length is also really big, the material is most likely going to fracture. Okay, so you're just manipulating this equation, you're moving it around and just applying below or above the curve. Okay. Okay, so let's do an example where, so let me get this on Top Hat. So if you have a large plate that's a steel alloy, and it has a plane strain fracture toughness. So this is your K1C. And your book goes into nuance details about what a plane strain fracture toughness is. But it has to do with the dimension of the material. If during service the plate is exposed to tensile stress, so that's your applied stress of 200 megapascal, determine the minimum length of a surface crack that will lead to fracture. So note this is a surface crack, okay? And assume that y is 1. So this is the fracture toughness of a material. This is the applied load. What do you think is going to happen? In terms of how long does this crack have to be for it to lead to fracture? Okay, let me go back to the question in case you need that, although I don't think I showed the equation. Or also, there's A through E. So here's the equation if you need it. Remember, it's a surface crack. This should be y. This should be 1. Okay, let's see how we're doing here. All right, almost there. So let's get all your answers in. Yeah. Oh, it is different from Top Hat? Wait, you're supposed to determine A. Oh, I apologize for that. All right, so let me go back then. Sorry. Well, whatever's on Top Hat, should be. Okay, so 154. Let's get your answers in. Okay, last 12 people. Let's get your answers in the next 10 seconds so we can discuss it. Okay, about 6 more people. Let's get your answers in. All right, 5, 4, 3, last 4, 2. All right. Okay. Was there an audible O? Do you want me to open it to get your answers in? Okay. That's not a related O. Okay. So it's 24. So let's see. Okay. It is a straightforward calculation, but the emphasis on whether or not it's an internal crack or a surface crack, right? So that was sort of given. So you know your fracture toughness is K1C, right? It's uniaxial. That's what the 1 is for, critical crack. Okay, so it's 55 megapascal square root meters. So then you have to calculate what A is, okay? And so there you convert the units of meters to millimeters. It's 24 millimeters. So if you switch this equation around, you have your K1C over square root pi, sigma, all of that square root because your A was in the square root before. Plug in your fracture toughness, your applied stress of 200 megapascal, and you get that. Okay. All right. What about if your material now is replaced with a material with a higher fracture toughness? What can you say about the material? So I'll open that up. Okay. All right, let me clear. Let me just clear. Okay. I think this doesn't like it so much. Oh, my. All right. It's not clearing all at once. Not really sure why. Disregard the blue markers. Will the component withstand longer cracks without experiencing fast fracture, shorter cracks? Or will the component withstand lower stresses without fast fracture? Will the material not fail by fatigue now that you have higher fracture toughness? Or will the component not fail by creep? You're welcome to talk to your neighbor and consult. All right, we're just about there. Okay, last 9 people, 8 people. All right. Let's get your answers in 5, 4, 3, 2. Last chance, the last 5 people. All right. Okay, let's see. Wow, fabulous. Right, so anybody care to share since 90% of you got it correct? Sure, Kevin.
My logic was that since the material has increased its toughness, that means basically it can handle more stress, which means if the cracks were longer and thus the holes
Yeah.
by the patient we just had, the stress, overall stress was increased, it would be able to handle it.
Right, so the same strength, yeah, but higher fracture toughness. Yeah, so it can withstand higher, longer crack. Certainly, right, fatigue, we don't know how many times it's been cycled. That's irrelevant or insufficient information Creep is temperature dependent and also static load over time, irrelevant, insufficient evidence as well. So, right, so we're talking about crack length. And of course, it can higher fracture toughness, obviously directly proportional to A, so absolutely. Okay. This is manipulation of the equation again, so I'll leave that to you to practice. Right, now let's talk about cyclic loading. If you operate well below the tensile strength of a material, if given enough time and number of cycles, your material can fatigue and fail. Okay, and here you see it can also lead to fracture. And so the way we look at this fatigue and the way we calculate fatigue is we look at the mean stress. So if you're applying your sigma, it could be in tension, it could be in compression. If we take the average of that, so we add the two together, divide it by 2, that's the mean, right? That's the average. Then we can also take a look at what's called the stress amplitude, and that's the difference between your max and your min divided by 2. So that's noted in the materials community as S, not sigma, S. Okay, so you can take a look at a material's mean stress over time. That's this line right here. And you can also take a look at its stress amplitude over time. Both will be indicative of, you know, how the material will fail under cyclic loading over time. Okay. So it would look something like this. If you take a look, if you plot the applied stress, S, and then the number of cycles to failure, you could see that if you apply very high stress, that's very close to your tensile strength, you're not going to last very long. Here it's 100 cycles. The material is going to go in, out, or, you know, whatever, however it's being used in service, it's not going to last very long. If you want it to last much longer, you can reduce the applied stress, and under cyclic loading, you could see here, you know, 10 to the 5th, 10 to the 6th. There's a limit in which you can safely say, the material will probably not fail or have a much longer cycle life to failure, and that's this fatigue strength or endurance limit. So if you operate below this threshold, let's say, for your material, for this particular material with a tensile strength of this value, most likely it will not fail in your lifetime or in the number of cycles that you can track. That's extremely generous and theoretical. Most of the time, what you really, once again, the error bars are like this. So I can safely say, if you're going to apply this stress, your material, I can probably guarantee a lifetime of 10,000 cycles, you know. Okay. If you apply this load, your error bar is probably like this. So it could fail 10,000 cycles in, or it could fail, you know, all the way out here, or some infinite time. It might not fail. It might be, you know, really long. So I would treat this, you know, I would be very cautious about operating around this regime. So even though this is the endurance limit, the error bars are quite large when it comes to this region. So that's, take it with a grain of salt, okay? Same, you can plot the same curve for different materials. Here's a steel. It has this more elbow type behavior. For aluminum, as you could see, there's no really definite, where does the endurance limit begin? Maybe if you elongate it, maybe this is your endurance limit versus, you know, up here for steel. So not all curves, not all materials are the same, and they can behave quite differently, okay? So that's just something to keep in mind. As I mentioned, crack growth can accelerate. So your small crack, if it becomes longer, it's not a linear elongation. It's not 2x and 3x. It could be 1x, 2x, and exponentially grow, as you can see here, okay? So that's something to keep in mind. Let me talk about the ways we can strengthen material and work around, you know, or lengthening the lifetime of the material. There's carburizing, and you can carburize, as in the example of diffusion that we've talked about. You can just carburize the layer so that it's strong right just right at the surface, and it protects everything else in the bulk. There's a mechanism called shot peening, and basically you're just accelerating like a stainless steel ball to your material and just deforming your material before it can deform itself. That's one way. Now there's what's called laser shot peening. It's cool. You basically have a high power laser and you do the same thing. You apply the same amount of stress, but here it's with a laser source as opposed to like some stainless steel, ball bearing. It is very cool, and it originated actually here up the street in Worthington. So it's very revolutionary in terms of manufacturing technology. The takeaway from these slides is sharp corners are stress concentrators and not advisable. If you want to decrease the stress concentration, you can see we changed the curvature. This is much better. Okay, if you're designing a component, this is something that you would want to keep in mind. Let me see. Okay, let me see. So you can take a look at fracture toughness databases. These are what's called Ashby plots. You can take a look at fracture toughness versus strength of a material, and you could see, okay, what material is strong and also can absorb a lot of energy. Those are typically metals. So all these examples here, fracture toughness very high, whereas let's say polymers, they're quite low, but they are ductile. So it's always a trade-off, right, in terms of mechanical properties. Okay, let me end here. This is a summary of the failure types and also what characteristic properties one would discuss. Professor Jennifer Locke will be coming to give a lecture. She will also have top hat questions, and she'll tell you all about the world of corrosion and failure that way. Okay.